Hi everyone, let's wrap up chapter 7. The new stuff I talk about in this video is optional. Now, back in the early parts of chapter 7, we talked about solving systems of equations. The equations correspond to graphs, like the line in black here and the snake in blue, and we looked at these intersection points, which were solutions to the system. Now, in your calculus class, Math 150, you might ask questions like, what's the total area between the black graph and the blue graph? The area of this region plus the area of this region. And sometimes you can use symmetry. You need to know where these intersection points are in order to set up the integration. Use integration to find areas. And also, in Math 150, you're going to do things like take these regions, revolve them about the y-axis, let's say, and you're going to get a three-dimensional solid. And you'll use integration to find the volume of that solid. Okay, a few more comments. How do you graph x squared plus y squared equals 1? We saw him earlier in the chapter. That was the unit circle, was centered at the origin. But how do you graph an inequality? How do you graph x squared plus y squared is less than 1? You graph the interior of the circle. And how do we know to graph the interior? Well, you could test points. Remember, x squared plus y squared equals 1 corresponds to the boundary, which is dashed now. It's technically excluded from the graph. This represents the solution set to this inequality. Infinitely many points here in the interior. You could test points. So the origin, for example, 0, 0, x equals 0, y equals 0, 0 is less than 1. The origin, 0, 0, satisfies this inequality, and that helps tell us that we're going to shade in the interior. What about the exterior? Take a point like 2, 2. If you plug in x equals 2 and y equals 2, that's going to fail the inequality. You do not shade the exterior of the circle. So you could use a test point method. The origin satisfies the inequality. You shade the interior. The point 2, 2 fails the inequality. You do not shade the exterior. Or if you wish, you could test 1, 1, which is also in the exterior. By the way, what if you do is less than or equal to? You press is less than, and then right after that, the equal sign, you get is less than or equal to, and you get not just the interior, but the actual boundary, the actual circle. The circle will also consist of points that satisfy this inequality, this weak inequality, where you allow the circle. Oh, what's x squared plus y squared is greater than 1? That's the exterior of the unit circle. Okay, now let's consider Geogebra. 3 dimensions. How do you graph x squared plus y squared equals 1 in 3 dimensions? It's not just a circle in the xy plane. You slide that circle parallel to the z-axis. In fact, the z-axis is going to be the axis of this cylinder. You get a cylinder. Basically, you have the unit circle, but then z can be anything above and below the unit circle. What about this? X squared plus y squared plus z squared equals 1. That gives you the unit sphere centered at the origin. You will definitely see these guys in calculus. Calculus with analytic geometry. By the way, if you replace this with is less than, you get the interior of the sphere. But GeoGebra doesn't do that, I don't think. All right, back to Desmos. How do you graph x equals 0? X equals 0. That's the y-axis. But how do you graph x is greater than 0? That's everything to the right of the y-axis, right? All the points whose x-coordinate is greater than 0. How do you graph? Let's make it is greater than or equal to. Then you pick up the y-axis. How do you graph y is greater than 0? What's y equals 0 first? How do you graph y equals 0? That's the x-axis. If you make this y is greater than 0, that's everything above the x-axis, where all the y coordinates are positive. Notice right now that that this piece here is dashed, but if you make this is greater than or equal to, then this is no longer dashed. The whole x-axis is solid. Now, if you solve a system of inequalities, that means we need the overlap. What's the overlap between the red shaded area and the green shaded area? It's this dark green shaded area in quadrant 1, together with the non-negative x-axis and the non-negative y-axis. So all the points in here, including on these rays here, all of these points will give us the solution set for this system of inequalities, overlaps. Just like if we dealt with curves, we wanted the overlaps or intersection points between curves. When we're intersecting these regions, okay, we get a region of intersection here, which is the solution to the system of inequalities. We could do more. We could do something like x plus y is less than 1, for example, okay? And we can throw in some more inequalities, like, for example, linear inequalities. For example, let's throw in x is less than 2. Whoops, x is less than, how about 0.5? X is less than 0.5, and focus on this trapezoid in here. So we can throw in some more linear inequalities, and we get these regions of intersection with these linear boundaries. And that takes us to linear programming, which is covered in like Math 116. All right, in linear programming. So if you have a bunch of linear inequalities and you solve that system, you might get a region like this with linear boundaries. The x-axis could be production of guns. The y-axis could be production of butter, guns versus butter. Now, bear in mind, given the amount of money we have, we can only purchase certain ordered pairs, guns and butter. This is called the feasible region, what we can possibly buy. Now, the profit function at each point, okay, so each point corresponds to some profit. If the profit function itself is linear, then it turns out that the optimal point, the optimal production point, will correspond to a corner point, guns, comma, butter. Or you could have ties along an edge. That's a key principle of linear programming, which is a key process of optimization. How do you optimize profit given these constraints? So just some ideas from chapter 7.